AP Chemistry Unit 2 covers structures and properties of chemical compounds. You'll be diving deep into the ways that chemical compounds are ordered and the bonds that hold them together. Hi there, my name is Jeremy Krug and you've found the place for all things AP Chemistry. You're about to learn the 10 most important things you've got to know from Unit 2. If you're new here, welcome to my channel. Take a look around, check out my AP Chemistry playlists, that's where the action is, and make sure you subscribe because I don't want you to miss a thing this year as you're learning chemistry. If you learned something from this video, remember that one of the greatest compliments you can give me is to tell your friends about my channel. And if you're serious about getting that 5 on the AP exam in May, check out my ultimate review packet for AP Chemistry. It's got the full review videos for every unit, complete study guides, practice questions, my exclusive tips and tricks for each unit, and 2 full practice exams in the AP exam simulator. And as a special gift to you, everything for Unit 2 is part of an absolutely free trial you can get over at ultimatereviewpacket.com. Now, here are the 10 things you've got to know from Unit 2. Number 1. A chemical bond between a metal and a nonmetal is ionic. A chemical bond between 2 nonmetals is covalent. The greater the difference of electronegativities of the 2 nonmetals, the more polar the bond will be. Imagine we have a metal, sodium, and a nonmetal, fluorine. Metals usually donate electrons to nonmetals like we see here. Sodium now has a positive charge, and fluorine now has a negative charge. These ions now have an electrostatic attraction between them, allowing them to form an ionic bond. Remember, a metal and a nonmetal forms an ionic bond. However, with 2 nonmetals like selenium and fluorine, those form a covalent bond. Since carbon and phosphorus are also nonmetals, they'll make a covalent bond too. Some pairs of atoms are better at sharing electrons than others. If we have 2 atoms with very different electronegativities, like selenium and fluorine, that will be a polar covalent bond, since one of the atoms is hogging the electrons, causing electrons to be shared unequally. On the other hand, carbon and phosphorus have very similar electronegativities, so the electrons in that bond are being shared almost equally. This is called a nonpolar covalent bond. How can we tell if 2 atoms will have polar or nonpolar bonds between them? Since we're not given an electronegativity chart on the AP exam, we have to estimate using the periodic table. Notice that selenium and fluorine are relatively far apart from each other on the periodic table. That tells us their electronegativities will be quite different from each other. On the other hand, carbon and phosphorus are neighbors on the periodic table, so their electronegativities are very close to each other. Let's practice. Sulfur and bromine are both nonmetals, so that's a covalent bond where the 2 atoms share electrons. Iodine and fluorine are also both nonmetals, so that's also going to be a covalent bond. Magnesium is a metal, oxygen is a nonmetal, so this pair of atoms forms an ionic bond. We can estimate the polarity of the covalent bonds with the periodic table. S and Br are right next to each other, so that indicates a nonpolar bond. On the other hand, iodine and fluorine are relatively far apart, which indicates a polar bond. Number 2. A bond length will be at the position where the potential energy between 2 atoms is the lowest. The bond energy is the energy required to separate the atoms at that condition. On the AP exam, you'll likely see a graph like this, where the potential energy between 2 atoms as a function of distance is shown. When you're asked to determine the bond length, focus on the very bottom of this curve. The distance between the atoms at the bottom of that curve is very close to 230 picometers, and that's the bond length. To find the bond energy, we'd focus on the y-axis at that same lowest point. It's right at 200 kilojoules per mole. Bond energies are always positive numbers. The reason it's negative on the graph is that this is the energy released when the bond is formed. We're being asked to find the energy required to break the bond. Number 3. Bond lengths can be predicted by considering the atomic radii of the atoms participating in the bond. Triple bonds have the shortest bond length and the strongest bond energy. Single bonds have the longest bond lengths and the weakest bond energy. Let's compare the bond length of F2 and Br2. Remember that back in Unit 1, we learned that fluorine has a smaller atomic radius than bromine, as predicted by seeing that fluorine is higher up on the periodic table and has fewer electron shells. Since the atomic radii of the atoms are smaller, the bond length between the atoms will be shorter. So when atomic radii are greater, the bond length between the two atoms will be greater. So the fluorine molecule has a shorter bond length than the bromine molecule. And this is confirmed by the numerical bond lengths that we can find for these two molecules. When comparing multiple bonds, remember that single bonds are the longest, double bonds are shorter, and triple bonds are the shortest of them all, as demonstrated by these 3 carbon-carbon bond types. If we're comparing the energy of bonds, single bonds have the least bond energy, double bonds have a higher bond energy, and triple bonds have the highest bond energy of them all. Sometimes we call this bond order. A bond order of 3 just means it's a triple bond. A bond order of 2 refers to a double bond, and a bond order of 1 refers to single bonds. Number 4. Coulomb's law can be used to predict the relative melting points of ionic compounds. The higher the magnitude of charge, the higher the melting point will often be, while ions centered closer to each other will also likely have a higher melting point. The ionic compound sodium chloride has a melting point of 801 degrees Celsius. Magnesium sulfide has a much higher melting point. That's because the two ions have a greater magnitude of charge. A +2 and -2 ion pair will have a much stronger attraction than a +1 and -1 pair. In the case of aluminum phosphide, there's a +3 and -3 ion pair, and notice that its melting point is even higher. The melting points of ionic compounds usually increase as the magnitude of their ionic charge increases. What if it's a tie, and we have ionic compounds with the same ionic charges? In that case, look at the atomic radii of the ions. Lithium fluoride has a melting point of 848 degrees Celsius. Sodium chloride, just like lithium fluoride, also contains a +1 and -1 ion pair. But notice that in sodium chloride, the ionic sizes are larger, and since the ion centers are farther apart from each other, the coulombic attractions between the ions are weaker, which explains why this compound has a slightly lower melting point. Potassium bromide is also a +1 and -1 ion pair, but this time the ion centers are even farther apart. And because of that, the melting point of potassium bromide is even lower. Remember, coulombic attractions are weaker when the centers of those ions are farther apart. Number 5. In an ionic compound, cations and anions are arranged in such a way so that positively and negatively charged particles are as far away from each other as possible. This image represents the crystal structure of an ionic compound, sodium chloride in this case. The positive and negative charges arrange themselves in such a way so that the positive ions and negative ions are closer to each other, since opposite charges attract. At the same time, ions of like charges are as far away from each other as they can be. Can you identify which ion is sodium and which one is chloride? Remember, anions are usually larger than cations, so the green spheres would represent chloride ions, while the purple spheres would represent sodium cations. Number 6. There are 2 types of alloys, substitutional and interstitial. In substitutional alloys, atoms of an element with a similar atomic radius substitute into positions held by the host metal. In interstitial alloys, much smaller atoms squeeze themselves into the interstitial spaces between atoms of the host metal. Substitutional alloys include most alloys that you've probably heard of, like bronze, brass, and pewter. In substitutional alloys, atoms of similar sizes substitute into positions of other elements in the alloy. On the other hand, in interstitial alloys, much tinier atoms literally stick themselves into the interstitial spaces between atoms of the main metal. The best example of this is steel, in which tiny atoms of carbon get in between atoms of iron, which happens to be much larger than carbon. Those carbon atoms act as a hardening agent. Remember, in substitutional alloys, the atoms have approximately the same atomic radius. In interstitial alloys, one of the elements has a much smaller atomic radius than the host metal. Number 7. When drawing Lewis electron dot diagrams, try to observe the octet rule, where atoms tend to have 8 valence electrons. However, when necessary, atoms with 3 or more electron shells can have an expanded octet. If we're trying to draw the Lewis electron dot diagram for the carbonate ion, we place the central atom, carbon, in the middle. We can draw 3 oxygen atoms surrounding that atom. We can place dots representing valence electrons around these atoms. According to the periodic table, as we learned in Unit 1, every oxygen atom has 6 valence electrons. So 6 dots go around each of the oxygen atoms. Then we add 4 valence electrons for the carbon, since carbon is in group 14. Since this ion has a -2 charge, we have to add 2 bonus electrons to the structure. A pro tip: start adding dots to the outside of the structure and work your way toward the middle. It's a good way to prevent mistakes. We try to give every atom 8 valence electrons following the octet rule. The carbon has only 6, so to give everything an octet, we can move 1 pair of electrons from the oxygen atom and move it to the middle, making a double bond. Now everything has 8. So the finished Lewis structure looks like this. We have 2 single bonds and 1 double bond. Anytime you draw the Lewis structure for a charged ion like we have here, remember to place brackets around the structure and write its charge. Notice that you could have placed the double bond on the left-hand oxygen or on the right-hand oxygen. It really doesn't matter. All 3 of these structures are correct. Multiple Lewis diagrams that are all correct, like these, are called resonance structures. This particular ion has 3 resonance structures. How about this molecule? In SF4, sulfur goes in the middle with 4 fluorine atoms surrounding it. According to the periodic table, every fluorine atom has 7 valence electrons, so 7 dots go around every fluorine atom. Sulfur brings 6 valence electrons to this structure, so we'll put 1, 2, 3, 4 valence electrons. And you might notice that we don't have any room to place 5 and 6. So what do? Well, in this molecule, sulfur will have an expanded octet, which means it has more than 8 valence electrons. So for this molecule, we place those last 2 valence electrons as an unshared pair on the central atom. So this structure has 4 single bonds and 1 lone pair on its central atom. Number 8. Formal charge can help decide which Lewis diagram is a better representation for a molecule. Structures in which more atoms have a formal charge closer to 0 tend to be more favorable. And the formal charge of all atoms in the structure should add up to the total charge of that structure. Looking at the nitrite ion, NO2 with a -1 charge, 2 students might draw its Lewis diagram differently. We use formal charge to determine which of these 2 structures is more likely to exist. To determine the formal charge for the nitrogen atom in the first structure, we take the number of valence electrons that element is predicted to have according to the periodic table, which for nitrogen is 5, since it's in group 15, and we subtract the number of valence electrons assigned to it. Every electron in a lone pair counts as a 1, while every bond touching that atom also counts as a 1. So for this nitrogen, we have 1, 2, 3, 4, and the double bond counts as 2, so that's 5 and 6. So we subtract 6, and that's a formal charge of -1. We do the same thing for every other atom in the structure. This first oxygen brings 6 electrons according to the periodic table. And how many are assigned to it? 1, 2, and 3 total bonds makes a total of 5. So this first oxygen has a formal charge of positive 1. The second oxygen brings in 6 valence electrons, and it has 1, 2, 3, 4, 5, 6, and 1 bond, a total of 7 assigned to it, giving it a total formal charge of negative 1. What about the other structure? This oxygen has 6 valence electrons, and it has 1, 2, 3, 4, 5, 6 assigned to it for a formal charge of 0. Nitrogen has 5 valence electrons, and it has 1, 2, 3, 4, 5 assigned to it for a formal charge of 0. And this oxygen has 6 valence electrons, and it has 1, 2, 3, 4, 5, 6, and this bond makes 7. So it has a formal charge of negative 1. And this tells us that the second structure is more likely to exist, because structures where more atoms have a formal charge of 0 tend to be more favored. Number 9. Every central atom in a Lewis diagram can be described by a specific molecular geometry and bond angle. Students need to learn these geometries and bond angles. Students need to be very familiar with this chart for determining molecular geometry and approximate bond angles of any central atom in a molecule. The first 6 are the most common. They're found in structures that follow the octet rule. These last 6 are found in structures with an expanded octet. For example, in SF4, sulfur is touching 4 other atoms, and it has 1 lone or unshared pair, which means its geometry will be seesaw, with bond angles of about 90 and 120 degrees. In this next structure, the central carbon atom is touching 3 other atoms, and it has 0 lone pairs, which tells us it's trigonal planar with a bond angle of 120 degrees. Many molecules have multiple central atoms. Every one of these central atoms has its own geometry and bond angle. For example, in this molecule, carbon number 1 touches 2 atoms with 0 lone pairs, so it's linear with a 180 degree bond angle. Carbon number 2 is also linear with a 180 degree bond angle. Carbon number 3 touches 4 other atoms with no lone pairs, so it has a tetrahedral geometry with a 109.5 degree bond angle. Number 10. In any molecule, a central atom with 4 electron domains will have sp3 hybridization. A central atom with 3 electron domains will have sp2 hybridization. A central atom with 2 electron domains will have sp hybridization. To determine the hybridization of the central nitrogen atom in this structure, notice that the nitrogen atom touches 2 other atoms with 1 lone pair, so it has a total of 3 electron domains. Any central atom with 3 electron domains has an sp2 hybridization. And just like before, any structure with multiple central atoms will have a hybridization for each one of those central atoms. Carbon number 1 touches 2 atoms with 0 lone pairs, so that's 2 electron domains, giving it an sp hybridization. Carbon number 2 is the same way. It touches 2 other atoms with 0 lone pairs. That's 2 electron domains, sp hybridization. Carbon number 3 touches 4 other atoms with 0 lone pairs. That's a total of 4 electron domains and a hybridization of sp3. And that's it. Those are the 10 most important things you've got to know from Unit 2. Remember that I have much more in-depth content for every one of the 91 topics in AP Chemistry right here on my channel. Go over to Playlists and look for the AP Chemistry Full Course playlist. And if you're looking for review and practice that goes beyond what you'll find on AP Classroom, my Ultimate Exam Slayer for AP Chem has 60 AP-style multiple choice questions and 3 full free response questions for Unit 2 and for every one of the 9 units. That's way more than AP Classroom. You can get my Exam Slayer along with the Ultimate Review Packet, and you'll have everything you need to succeed this year in AP Chem. Go check it out over at ultimatereviewpacket.com. Thank you so much for watching. Thanks even more for subscribing. Keep up the good work. You're going to do great this year. I'll see you next time.